Сидя, воспринял.
Ну, правильно. Ну, кто-то не любит сидеть, любит стоять и щелкать, кто-то любит сидеть. Ну, вот мышка есть. Есть эта штука, я не знаю, она работает. Ну, короче, если будешь сидеть, то мышку проще всего.
Там есть.
Пока нету. Но вроде бы Миша портной ничего.
Может, я раньше люблю.
Очень сильно будет.
Да, не надо. Нет, я люблю.
Кто-то все.
I'm living with language, maybe it makes sense to discuss.
Yeah. Прям по-русски.
You read it?
Фамилия, потом. Не знаю. Они просто
No, okay.
по-русски.
All the slides, все слайды.
Yeah, all the slides in Russian, unfortunately, but well, I will speak English.
Actually,
At least I will try.
not all. Not all slides.
Well, I think the title is okay.
For example.
For example, it's mixed. So I hope everything will be. So,
Сейчас тут не будем ждать. Пусть мне escape. Ой. Сейчас давайте, да.
Формирование началось.
Ага. Антон, нажми дополнительно и при перемещении. Видите снизу, видите снизу. Yes, today we have a guest from Solid State Institute in Chernogolovka, Anton Shchepetilnikov, who will speak about something in quantum Hall regime.
exactly.
So, Anton, you can start.
Okay, thank you for the introduction. My name is Anton, and I work in the Institute of Solid State Physics in the group led by Professor Pushkin. So I haven't got much of an opportunity to speak English, so possibly it will be a little rough at first, but well, I hope everything will be quite understandable. So my talk today would be about different phase transitions in the regime of the quantum Hall effect. So here is the plan of my talk. So I will start with a little introduction, and then I will talk a little bit about the experimental method and the samples, and then we will discuss our main results. So I would like to start with the quite well-known concept of Stoner ferromagnetic transitions. So it was well predicted in the first half of the 20th century, and that the electron-electron interactions, strong electron-electron interactions, even in the absence of the magnetic field, they impose the spin polarization of the 2D electron system. So if we enhance the interactions, then at some point the system becomes spin polarized. So this concept, it was introduced, well, tens of years ago, but experimentally it was realized, I think, like 2 or 3 years ago, mainly because of the, well, the need of very high quality samples. So before I will go on, I would like to speak a little bit about what is how we can enhance the electron-electron interaction. So what is the strength? How can we measure it? The basic idea is to dimensional electron system to compare two typical values, like the characteristic Coulomb energy, the energy of Coulomb repulsion between electrons, and the characteristic kinetic energy of electron movement. In the case of 2D electron gas, that would be Fermi energy. If we measure this ratio, if we introduce this ratio, this ratio is on the slide. So, and we can see that it is inversely proportional to the square root of electron density. So we can enhance the role of Coulomb effects by decreasing the electron density, or we possibly should take electron systems with specific band parameters. So the higher the effective mass, the higher the effective band single particle mass, the stronger are the electron-electron interactions. So if we're talking about two-dimensional electron systems, epitaxial ones, we may look at the ones that are indicated on the slide, like zinc oxide heterostructures with the effective mass 0.3 of the free electron mass, aluminum arsenide quantum wells, so the effective mass is even higher, and possibly silicon with a slightly reduced mass. So basically, these three epitaxial structures, they are the material systems where, well, the physics was, the Stoner transitions were observed. So as I have told earlier, we can start with the ferromagnetism at zero magnetic field. For example, this is a recent work made in the group of Mansour Sheygan in 2020. So the idea was to take a very high quality aluminum arsenide quantum well with strong mass. The parameter RS is, for example, indicated here on the right side of the figure. Here is the electron density in 10 to the power of 10. So it's really very, very small density. And by gating the structure, this group was able to achieve really, really low densities. And what they actually measured, they measured the dependence of the sample resistance, longitudinal resistance, for various magnetic fields, but the magnetic field was completely in the plane of the structure. So if we start from zero field and gradually enhance the magnetic field, at some point the Zeeman energy becomes higher than the Fermi energy. So when we travel here, some part of the electrons are transferred from the lower parabolic band to the upper one, and the resistance slowly changes. But at the point where the system is fully spin polarized, so the spin polarized parabolic band is much higher, and the Zeeman energy is much larger than the energy splitting is much larger than the Fermi energy, then the resistance will stop growing with the magnetic field. It will become almost flat. So this is exactly what we see here. So at first it grows, and then when the system is spin polarized, it becomes flat. So if we enhance the ratio, or if we reduce the electron concentration, the magnetic field at which the system becomes spin polarized, it slowly diminishes. And at some point, this feature well, it vanishes. And the authors of this work, they attribute this vanishing to the stoner transition, to the ferromagnetic phase transition. So all the electrons become spin polarized, and well, applying magnetic field does nothing. So this is the zero magnetic field. Similar results were acquired in 2022 in the so the phase diagram, it is here. So there are two actually parameters. So first is the spin polarization of the system, and second is the spatial configuration. So what do we see? Is it metal, Fermi liquid? Is it the first one is paramagnet or ferromagnet, and the second one is like Fermi liquid, possibly metal, insulator, and at some point it becomes Wigner solid. These parameters, these ratios are really very high, and actually there were a number of papers where these parameters were calculated using like Monte Carlo algorithm, and these are consistent with these calculations. And actually, the samples are really very clean there. So they
just speculate that they have these phases.
Yes, exactly.
Devices.
Yes. So
because of some calculation shows that for this.
Yeah. So the idea is that experimentally they see these. Actually, I do not recall. So possibly it is. Possibly they did some IV characteristics of the Wigner solid, and possibly they were able to extract some information. But I'm not sure. I have to look more carefully in the paper. So similar results were performed were acquired in zinc oxide heterostructures. So this was made in the group by Jürgen Smet in Stuttgart in 2022. So this is the paper. So basically they did the same thing. They actually measured how the resistance evolved with the magnetic field, with temperature, and with concentration. So this is the color map. So it's not really that informative as before, but you can see once again that here is the range of small concentrations, and here it is almost resistance, and here it is almost flat. So here is once again the calculated phase diagram. So we can have some paramagnetic fluid, spin polarized Wigner crystal. So here is some other phases, possibly, I don't know. And once again, spin polarized Fermi liquid, spin polarized Fermi liquid on these two sides. So you can see that the parameters of the sample are really they are clean, and the electron concentration is really low. So these samples are unique. So it's like almost only two groups in the world have the access to such quality samples. So of course we don't have an access to such samples, and we have to do something we can. So the idea is as follows. So we can try and apply the perpendicular magnetic field to the structure. And in this case, for example, it is well known that the spectrum of the two-dimensional electron system becomes quantized in the set of Landau levels that are split by the spin and possibly by some other degree of freedoms. And the idea is that if we work at some small filling factors, so small amount of Landau levels is populated, so the electrons, they actually don't have the kinetic motion. So they actually live on this one Landau level, and to to get on the other Landau level, they have to spend a lot of energy. So in some sense, it freezes this kinetic motion. And instead of the electron Fermi energy, we now have to operate with this inter-Landau level energy like cyclotron energy or Zeeman splitting and so on. So the idea is to apply large field, and so we can observe, well, some really interesting electron interaction induced physics. So the idea is really not new. So for example, applying large magnetic field and making the electrons reside on the lowest Landau level, for example, allowed to observe fractional quantum Hall effect, which is, well, purely electron-electron in nature. And possibly, and even Wigner crystallization was observed at some, well, subunity filling factors as well. So really, this concept works. So if we apply large magnetic field, we see the enhancement of electron many particle physics. So what we would like to see then, if we are talking about these ferromagnetic phase transitions. So the first idea was, okay, we can look at the even filling factors where both spin branches of one Landau level are fields and the system is unpolarized. And we would like to capture the phenomenon that the system becomes spin polarized under certain conditions. So, for example, the state was unpolarized by the spin and it becomes spin polarized. So this is what we would be looking for in the next part of the talk. So before I continue, I would like to introduce several key energy scales that are present in the quantum Hall effect regime. So the first one is actually quite understandable. This is the single particle distance between Landau levels, the cyclotron energy. The second one, so if we tilt the magnetic field to the sample surface by the angle theta. So this is this cyclotron splitting, which is sensitive to the perpendicular magnetic field. This is the spin splitting that is sensitive to the full magnetic field. This is the combination of the full magnetic field. And then there is the Coulomb energy. So instead of it in the quantum Hall regime, it becomes this combination. So the squared Coulomb charge, the electric constant, and the magnetic field length. This one, it depends on the magnetic field. So this is the typical distance between the electrons in the magnetic field characteristic. And actually, if we look at the effective mass and calculate these values, so this value is, for example, in aluminum arsenide, is like 5 times smaller than this Coulomb energy. And at this point, actually, a question arises. So the Landau levels, they are calculated for a single electron in a strong magnetic field, and no Coulomb interaction is introduced. So how can we speak about Landau levels if the Coulomb interaction between Coulomb repulsion between these electrons is much, much stronger than these single particle levels? Well, there is no strict theory about that, so no one actually knows if we can or if we cannot theoretically, but typically everyone says, okay, everything is okay. We can use this Landau levels picture, we can use the effective mass, we can use the effective G factors for Zeeman splittings, but they are renormalized compared to the band parameters. So this is similar to the Landau renormalizations, but well, the Landau theory about the electrons on the Fermi surface, about the quasi-particles, and how can we use it for well, theoretically for the description of the system is, I really don't know. However, if we start looking at the experimental pictures, then everything is okay. So here is, for example, the work by Viktor Solovyov from our group, where he measured the optical photoluminescence for a set of zinc oxide heterostructures starting from really small densities, and in strong magnetic fields. And so you can see that this is in zero magnetic field in photoluminescence. And if we apply magnetic field, we see these Landau level splittings. And so we can plot it. They are really linear in magnetic field. And we can extract, for example, effective mass. So the concept of Landau levels, at least experimentally to a certain extent, is actually works for these.
Can I ask a question?
Yes, sure.
From them? But what about there was this famous Kohn theorem that for say for cyclotron resonance interaction does not matter because center of mass separates and things like that. Isn't it the same thing?
No, it's not the same thing, but this concept is correct. So the Kohn theorem works. And if we actually measure the interaction of these structures, zinc oxides, for example, with the electromagnetic field, and we have done that, we observe the strict single particle effective mass in full accordance with the Kohn theorem. So this one doesn't is not violated here. So what we measure here is not the interaction of electron system with electromagnetic radiation. It is how we can possibly describe the strongly correlated Fermi liquid in the magnetic field. And the answer is we can try to use this effective mass and effective G factor, and everything is going to be okay. So in some sense, in some sense, this discrepancy stems from the fact that when we're talking about the cyclotron resonances, about like spin resonances that we would be talking later, we are measuring the dispersion of the excitations at the zero wave vector, because the wave vector of light is really, really small. But when we are talking about some transport properties and some macroscopic properties of the system, we are dealing not with these excitations, charge or spin excitations of the electron system at zero K vector, but rather at large wave vectors. And then we have to of course, introduce some renormalization. So the most possibly famous consequence of this effect is that in gallium arsenide, for example, if we're talking about the activation gap at the unity filling factor, the single particle splitting is like 20 times smaller than that observed experimentally from transport measurements. So, but if we measure spin resonance, we observe only the single particle G factor.
This 20 times reflects you said renormalization.
Well, in gallium arsenide, the energy splitting, electron interaction induced splitting is depends on the magnetic field like square root. Here, for some reason, the dependence is linear. We don't know why. Because, if we are talking about then influence of the electron-electron interaction, then we would expect this combination with the magnetic field length being proportional to the square root of the inverse square root of the magnetic field. So it should rise like square root of the magnetic field, and these are linear. For some reason, this one is linear. So really, I don't know. Okay.
Splitting between two neighboring peaks on the B panel equals to cyclotron frequency with effective value of effectiveness, or it doesn't?
Well, it is with the renormalized mass. Renormalized. So it's
how large is 20 times? Or?
No. So I was talking about gallium arsenide, where it was 20 times. So here is the renormalized mass for like the concentration 10 to the power of 11 would be like 0.8, and the patent mass is 0.3. So it is like 2.5, yes. But it's a lot, yes, actually, for the mass and for the splittings. Okay, so for some reason, the Landau levels survive, possibly the symmetry helps us, possibly not. And then we would like to find the way to detect these ferromagnetic phase transitions. So how do we experimentally understand that something happened with the system? So for a long time, the main idea was that we can try to measure the resistance of the sample by tilting the magnetic field, and at some point around different filling factors, a sharp spike rises. So it's hysteretic, like here around the filling factor 3 with the magnetic field, and it may be really strong. This is for zinc oxide, and this is for aluminum arsenide. So this is actually, I guess, in the early 2000s. Well, however, if we're talking about transport, we really can do much. So we can measure some activation gaps, we can capture this spike, but really we cannot understand fully what happens with the system. So we can try to do some optical studies. So this is a group by Anton V from our group, where he measured the evolution of the photoluminescence for a certain structure, zinc oxide, at tilted magnetic fields. And at some point he observed that tilting the magnetic field further, it actually makes the photoluminescence look different. So, and this was also interpreted as the phase transition. So yes. And if we are talking about the spin properties of the two-dimensional electron system, that they are macroscopically changed, we can try to use, well, what is specifically designed to probe spin properties of two-dimensional systems, so namely the electron spin resonance. And so this is exactly what I and my group of PhD students do. We measure electron spin resonance, and I would like to discuss later these results. So before I continue, I would like to demonstrate this figure from this work by Alexander Vankov. This is actually the phase diagram. So it demonstrates in the coordinates electron density and the tilt angle. So we can see that, well, if we fix the electron density and start tilting the magnetic field, at some point the system at the filling factor 2 becomes spin polarized. So this is, but what is even more interesting, that if we fix the angle and change the electron density, the same thing happens. Even for zero angle, at some point, at some critical concentration, like around 2 × 10⁻11, the system becomes, at this filling factor 2, spin polarized. Well, so even without any angles. So here is, for example, the combination as renormalized spin susceptibility, effective defect, and mass extracted from these positions. Well, you can see that it is almost 2 times, it grows almost 2 times in these.
How do you know you have spin polarization on this?
Okay, so how do we know that we have spin polarization? There are two. There are two key observations. So first, maybe second, I will show you later how the electron spin resonance evolves around these phase transition. And then there was a slightly earlier work also by Alexander Vankov, where he studied spin excitations by Raman scattering in this regime, and he demonstrated that spin excitations in this transition, they actually undergo a drastic change. So this is another evidence for the change of spin polarization. So, okay, let's turn to the electron spin resonance. Well, in the quantum Hall effect regime, the electron spin resonance is pretty much the same. So the system that is, well, spin polarized, it absorbs microwave or, well, sub-terahertz photons, and the spin is excited to the higher state. So, and then we have the spin here, the electron here, and we have an empty space here. So actually, this excitation, this quasi-particle, is very similar to exciton that is observed in semiconductors, and it is also often called spin exciton. And this dispersion, it was calculated by two groups independently, in Soviet Union, and by Kalin Galperin in the United States, I guess. This is the picture from, because in the Soviet Union manuscript there were no pictures, so this is the picture from this paper. So this is the dispersion. So energy vs the wave vector. So we see that it starts from zero, which means the energy is essentially single particle grows quadratically, and at large wave vectors it tends to some asymptote, which is actually some portion of the electron-electron interaction energy. So this is consistent with with the Larmor theorem, that when we measure the interaction with the spin ensemble and the light, then all the characteristic splittings should be taken as single particle. So how we can measure the electron spin resonance? So the classical concept is, okay, we can simply measure the amount of power absorbed by the electron system. However, this is really a great way to measure electron spin resonance, but for two-dimensional electron systems, there is a number of limitations. Namely, first thing, the amount of spins is really not that large in the two-dimensional electron system. So the idea is to, and it was first introduced by von Klitzing, I guess, in the 80s, that we can use the two-dimensional electron system itself as a bolometric detector of this absorption. So, for example, if we heat food in the microwave, then it absorbs microwaves, and its temperature rises. So the idea is pretty much the same. We can heat our sample, and its temperature will increase, and the increase of the temperature will lead to the increase of its resistance. And this is what we can actually measure. And the resistance we can measure with very high accuracy. So the concept is that we can use two lock-in amplifiers to extract these variation of the sample resistance under microwave radiation, but I will not go into much of a detail. So here is, for example, the typical spin resonances that were acquired for a set of frequencies starting from 134 gigahertz, and if we increase it, the peak actually travels with the magnetic field, so everything is great. So the method works perfectly. It allows us to perform really broadband experiments. So we can go up to 1 terahertz and start with as low as, I don't know, like 1 gigahertz, no problems. Okay, so first, now let's return to these phase transitions. First, let's find one. We take this zinc oxide structure with the density 2.2 times 10 to the power of 11, and we started tilting it. So we have pretty good Shchepetilnikov minima, and then at some point we observe a strong hysteretic spike here, and then once again there is a pretty good minima. And now we can start to measure the electron spin resonance here. Here we do not observe any spin resonances. Here we observe strong spin resonance. So here is the dependence of the amplitude on the filling factor here. And here we also measure spin resonance. And once again, here is the amplitude of the spin resonance around the filling factor. So we see that in this part, everything is pretty much the same, but when the spike comes, into play, this phase transition occurs, we see that the amplitude of the spin resonance drops, and we see almost no resonance. So this is a strong indication that what we observe here is indeed connected to the macroscopic change of the spin polarization of the system. Actually, okay, so we can try to compare the size of this spike. Okay, I must have missed why the spike comes to play as near the phase transition. I have skipped this. So the idea of the spike is that when the system transitions from one phase to another, the system becomes split into domains with different spin polarization. Of course, this splitting enhances dissipation. And so as the dissipation of electrons, these domain walls act like scatterers for electrons. As these actually dissipation in the electron system increases, the sample should demonstrate an increase in the sample resistance. So here is this slight increase, for example.
But I don't understand why do you have domains and domain walls, because you have homogeneous. Why don't you have homogeneously polarized sample?
Well, on the one side, so the idea is that here on this side of the transition, the system is homogeneously spin polarized. On this side of the phase transition, the system is homogeneously spin unpolarized. So how the system transitions from one state to the other. Another, funny thing about this is
domain is not between parts with different direction of polarization. Or polarization is
no, they actually do. So the domains are the grains of new phase in the old one.
But they have the same orientation of polarization, so spin vector.
Well, actually, I do not know. Possibly yes. But if it is tilted, well, I don't know. So at least they may sustain some electron spin resonance. So that is obvious from the experimental data. And this drop is really sharp. So the transition really is sharp.
Sorry, can I ask also? Usually, RxX increase of resistance, Hall resistance, longitudinal Hall resistance is proportional to longitudinal Hall conductance. Yes.
Yes.
So usually the sharp resistance like that means that there are spaces in the Landau level so that you can jump. It's not necessarily the increase in scattering, but usually kind of something change with the density of states on the Fermi level. It was no empty places, and then it suddenly they appear. No? Am I wrong?
Yes, this is one way to look at this picture. So the idea is basically what we can use as a basic concept of this phase transition. So, and what people usually use. So the first way to look at it is that we have these Landau levels that cross at the Fermi level. So these Landau levels, they are characterized by renormalized mass and G factor, and they cross at the Fermi level. So at this crossing, something happens. So this is there was a work by MacDonald in the 2000s where he demonstrated that when this thing cross, the system, actually is divided into these domains, and the characteristic size of the domains is like 10 tens of magnetic length, which is actually pretty close to what we estimate from our spin resonance data. Yes, so you can look at it that two Landau levels came close. And then, of course, the dissipation increases because there is plenty of spaces where the electrons may scatter. So this is actually similar to the picture I have tried to introduce earlier. So, but the idea that these two levels simply cross, well, it's pretty easy to comprehend, but it's not fully correct, because if we look at this Landau level crossing, then we should understand why we still have this pretty much developed Shubnikov-de Haas minima. So this one actually is, so the gap is here, it's really deep and something like that. But if we say that Landau level cross, then the gap should be zero. So we should observe no minima at all. But this is not the case. So actually, when we so the basic picture is single particle. Then we introduce electron-electron interaction through the renormalization of G factor and mass. But this is not all. So when these once again cross, what is left only is the strong electron-electron interaction still. And this one actually, well, does something with these levels so that the gap doesn't close, so that the system is still has some energy gap and this, well, and this thing. So people usually look at it like
it's kind of repulsion between levels. Yes, if something
to
goes
some extent.
diagonal.
Exactly. To some extent, this is repulsion between the crossing levels due to the electron-electron interaction. But then if two levels repulse, then typically one would expect that how is the combination of levels well, constructed of initial levels or something like that. This I really don't know what this part. So this is actually a pretty hard to calculate problem, because the strong electron-electron interactions is really not that easy to calculate. So people usually do some exact diagonalization of a finite size ensemble of electrons, and they try to speculate based on this one. So okay, this I guess we have proved that this spike is indeed associated with the phase transition. And once again, this phase transition is associated with the building up of a strong spin polarization of the system. So we can do the same thing around the even filling, but this time we would observe odd filling, like for example, filling factor 3. So this time we would once again observe here zinc oxide at tilted magnetic field, this hysteretic spike. So it's really hysteretic, like a ferromagnetic phase transition, and we can try to look at the spin resonance in different phases. So indeed, if we look here, both phases here and here should have spin polarization, because here one at small angles, one level is spin polarized and two are completely spin unpolarized, and here all electrons should be spin polarized. So this is exactly what we see in this case. We see a strong spin resonance. Here we see it even stronger. But when we come to this region where this phase transition happens, we once again see that, well, the electron spin resonance vanishes. So we actually don't know what happens. So it becomes broader and then vanishes. We actually don't know why this happens, so this is not what we have expected. Possibly this has to do something with, once again, enhanced scattering, and possibly the spin resonance, it actually becomes broader, and maybe it just is really here broad, so we do not see anything. The spin relaxes too fast. So this is an open question for us. But, well, the idea is that we still can identify this phase transition. So, well, possibly now I would like to stop with the spin, quantum spin phase transitions, and I would like to talk a little bit about the case when there are additional degrees of freedom in the system. So if we are talking about aluminum arsenide, then it has 3 equivalent bands in the bulk. If we make a quantum well from this structure, So the idea is that we will introduce valley degree of freedom, and then we will observe similar phase transitions, similar to spin. We will observe similar transitions of this valley degree of freedom. And we will demonstrate how to measure it using electron spin resonance. So if we come from the bulk to the quantum well with a finite width, then this structure has reduced symmetry, and the reduced symmetry will make this degenerate in the bulk values, will lift this degeneracy. So in the white wells, the combination of strain and the size quantization, it will make these two in-plane values to be the lowest ones. So in the white aluminum arsenide wells with the width higher than 6 nanometers, these two wells are populated and they are equivalent. So we come at the point where in our system, aside from spin, there is a pseudospin, so another degree of freedom, valley degree of freedom, which marks at which valley the electron is at the moment. These valleys in the bulk aluminum arsenide are located at the boundaries of the Brillouin zone at these at these 3 points. Yes, so and the masses are actually real anisotropic, so 0.21 mass and 1.1 the other, yielding the cyclotron mass 0.47. So how we can prove that in white wells the electrons occupy the in-plane valleys, and for narrow wells the electron occupies the out-of-plane valley. We can measure the cyclotron response, so we can measure the cyclotron resonance, here it is shown, and we can measure the cyclotron mass. So here we see the band mass 0.26, consistent with what is expected from the band structure, and at some point we have a strong increase of the mass that is associated with the this that the band structure restructurizes, so the in-plane bands are now occupied. So this was in this work. Okay, so we will later work with the with 15 nanometer width, which is much larger than this critical value, so that we would not have to think about these, possibly out-of-plane values. So let's start with the, if it is possible to observe this valley ferromagnetism at zero magnetic field. So this is once again a work made in the group led by Shagan. So the idea is here how we can measure it. So the idea is that the anisotropic effective mass in the plane suggests that if we measure, so if we have only one valley, and if we measure the resistance of the sample in this direction and in this direction perpendicular to it, these resistances should be really, really different. The mass differs 5 times. So around something like that, 5 times should be expected for the mass, for the resistance in this direction and this direction. However, if both valleys are occupied, then the symmetry suggests that the resistance in this direction and in this direction would be equal. So the idea is to measure the resistance here and here, and to look how it changes with changing electron density and temperature. And it turns out that at the lowest temperature, like 300 milli-K, at a certain point, the concentration 6 times 10 to the power of 10, this strong anisotropy emerges. And this is associated with the polarization, with this valley polarization. So here, when there is anisotropy, the system is valley polarized, and here where there is no anisotropy, the system is valley degenerate. So this is the pictures from this work by Shagan group. Okay, the main idea So our main goal was, okay, so we know how to measure the resistance, but we don't have these structures, but and we need to add something extra to this science. So what can we do? And the idea is, okay, let's try to measure electron spin resonance response of these structures. So if we take this sample and well, put the magnetic field solely in the plane, we can rotate it with response to 110, and it turns out that the G factor here is anisotropic like mass, and here is anisotropic like mass. And if we orient the in-plane component of the magnetic field along this axis, so this is the axis where the strongest anisotropy between this valley and that valley should be observed, we observe two separate electron spin resonance. So here is the electron spin resonance from one valley, here is from the other. If we rotate it back to the symmetric one, then we see only one spin resonance. And the idea is, okay, let's orient the magnetic field like that, and now we have access to spin resonances of these two valleys independently. And let's try to analyze this amplitude and that amplitude independently, and well, try to make some assumptions about the valley occupancy and about their spin state separately. So this is the basic idea, that we can observe two spin resonances independently. So once again, okay, so how can we detect this resonance? So indeed, this is the first idea is, okay, let's start tilting the magnetic field without thinking too much, and possibly at some point the spike would emerge. And this is exactly how we did, because we were looking for spin phase transition, and well, we were actually lucky to observe that one here. And I have forgot to mention that sometimes even when the sample is grown perfectly, some internal mechanical strains, they make this valley not equal once again. So they live in this degeneracy, and there is a slight energy mismatch. So built-in valley polarization. It is on the order of 1 milli electron volt, but it will be enough for us to observe these phase transitions. So we start tilting the magnetic field, and at some point this spike similar to the spin polarization emerges. Okay, so but how do we know what is this phase transition? It may be spin transition or something like that. So we can try and utilize our method, so we can measure like spin resonance response here and try to compare what we see. And what we actually see, so on the one side of the transition, we see one strong resonance and almost no response where we would expect it according to the G factors. On the other side, we see two, well, they are slightly different, but two really strong spin resonances with almost equal amplitude. So when we come from here to here, something really happens. So first, we have checked that these resonances are indeed spin resonances. So we checked their position with respect to angles, magnetic field, and everything is great. So, and then we can try to introduce these parameters. So this is the normalized amplitude of one of them to the sum. And we can see that exactly at the location of the spike, so which is marked by this line, we see a transition from one valley polarization to the other. So this indeed is a valley ferromagnetic phase transition. And actually we were first who were able to observe it by means other than transport, to the best of my knowledge at least. And we were also, so typically they do not observe these spikes for the valley spin, for the valley ferromagnetic transition. So we were actually lucky to observe it. What is usually observed, I will show later. So
amplitudes
of spin resonances, yes, extracted. So this is the sum of two resonance amplitude, and this is one. So if it is one, then only one valley is polarized. If it's close to 0.5 or exactly 0.5, the two are equally polarized. So how does the in-plane magnetic field helps us introducing, how does it help us to observe these transitions? So this is the single particle picture. So this is one valley, and this is the energy splitting, and these are the Landau levels, delta E, EV. And this here is delta EV equal to cyclotron energy. So, but we need to change this delta EV to observe, well, for the spike to emerge. And there are two actually mechanisms. So first one is that the reflector anisotropy introduces under the in-plane magnetic field the slight change of the level positions. And this slight change of the slight change of energy minima enhanced by strong electron-electron interaction is really enough for us to observe the effect. The other mechanism, well, is that when we introduce in-plane magnetic field, it actually mixes the motion of electron in the plane and the motion along the growth direction. So in some sense, in the tilted magnetic field, the Landau levels and the size quantization bands are not separate. They are not independent. And this effect is also small. So here is the work that where it was measured, and but this is enough for us to look to capture this spike. Of course, we had to be lucky so that our initial energy splitting would be large enough. We had to be lucky, but well. So now we would like to talk about how the temperature will change this picture. So for a spin transition, there is the work by Shagan, where the spike, the evolution of the spike with temperature was captured. So this is the purely spin transition, and it turns out that its amplitude demonstrated here, it first grows, and at some point it becomes smaller, so it decreases with the maximum observed at some critical temperature, and its width as well. So it becomes smaller, and at some point it becomes smaller. So this data was analyzed by MacDonald, and he actually calculated this critical temperature. But I will come to this later. So let's do the same thing. Let's measure the dependence of the spike with temperature and try to analyze its amplitude and its width. So we once again see this. So in the width, we do not see any critical temperature, but in its amplitude, we see this critical temperature 0.9 K. Now let's try to do some spin resonance measurements. So we can see that above there is 0.5 and nothing really changes. Below, really nothing changes, so it's monotonic. And when we are around this spike, around this critical magnetic field, really there is a critical temperature when the system starts to become, well, very unpolarized. From very polarized to very unpolarized. And this critical temperature really coincides well with these critical temperature. So they are really connected. And we can now try to look at what we would expect, what value we would expect. So this is the theoretical prediction made by MacDonald. And well, this is the experimental for the spin phase transition. So it should be in the range 2 Kelvin, like 4 Kelvin, and we observe 1 Kelvin. So given the difference in the, well, in the degrees of freedom, in the structure, and so on, I think that this is a pretty good agreement between these characteristic temperatures. Okay, so I guess I will speak.
Whether they should agree with
I don't know. So actually, I don't know the works where this critical temperature was calculated for the valley degree of valley ferromagnetic transition. So, well, the logic is, well, pretty much the same. So it should be some fraction of these, but what fraction, nobody knows. So it's really, really small. So this is actually what is left of the electron-electron interaction after we have introduced these renormalizations and so on. So this is what is left. at this exact level crossing. So I would like to skip this because here we demonstrate that we can also see spin ferromagnetic transitions, not valley transitions, but spin in the same system at larger concentrations, and how we can capture it. So they are totally different. And well, as I have said, that to observe these effects, we have to be lucky. But well, we would like to control our life ourselves. So we have tried to control these valley splittings. So how can we do it? We can introduce the controllable mechanical strain in the structure. If we glue our sample to the special piezo stack and applying voltage to this device, it makes it go longer or go narrower, and this introduces the mechanical strain on the sample. Well, the strain gauge here, it actually measures the resistance in the Wheatstone bridge. So because the resistance changes really, really small, so the resistor becomes longer, its resistance changes, it becomes shorter, its resistance changes, so we can control it. So what can we observe? So here is, for example, by the introduced splitting by the applying bias in this work that was measured by the change in plasmonic frequencies and so on. So typical mechanical strain introduced is 10 to the power of -4. So it's at some point it's really small, but if we introduce larger, the sample just cracks. So, but this is enough actually to perform what we need. So here is, for example, how the Shchepetilnikov Haas minima evolves if we apply a set of strain. So at first it grows and then it becomes small once again with the maximum around 0 strain. So this is, for example, for the filling factor of 2. This is once again the spike, but now on the x-axis is not the magnetic field, but rather the voltage on the piezo stack. So and we can try to once again to measure the spin resonance response here and here. So here it is. You can see that here is one dominating and here are almost 2 equal. But of course, we cannot work with such signal. We don't want to try to analyze, to measure the amplitudes of these 2 resonances independently. So we can increase the electron concentration. So here is the magnetic field is here, and it will, of course, make the spin resonances go far one from the other. So and here is, once again, if we fix the magnetic field here and start measuring the longitudinal resistance with the applied voltage. So at first it grows, and then it will become smaller, once again spike, and we can measure spin resonance here, here, here. So here is 1, here are 2, here is something in between. So indeed, these phase transition, that we are now able to induce these valley phase transition by the applied strain. So here is the G factors that we demonstrate that this is indeed spin resonances. So this is the resulting picture. So it's 0 close to equal polarization when at one side, valley polarized at the other, and something in between coming due to this in plane magnetic field, possibly evolution on the other side. Okay. So, for example, here is once again the typical spin resonances for a set of voltages. So 1, 2, 2, 2, 1 once again. So we observe the full set of valley phase transitions in this system. Well, it's funny actually that if we compare the effect, so the spike is really small and it is really narrow compared to these. Well, to this scale, and we do not observe here a distinct spike in resistance if we change the magnetic field. So possibly this is because when we put the sample on this stack, we also introduce some inhomogeneities in the structure. Well, so I guess, yeah, ideally. So Perfect timing, because this is the last thing I would like to show.
See you.
Yeah, thank you.
I
Миша,
Yeah, I just have, I don't know whether it is question or comment. I did quite a lot of this spin polarized system in around Lifshitz transition when first Landau level from the second quantization. Imagine that you have two quantization subbands.
Yeah, this is exactly, yeah.
Yeah. Then you have first Landau level, ground Landau level from the second subband eventually crosses with first Landau
Yes.
level from a lower subband. And we did, it is quite cited. It was in 2002, several papers, Apalkov Partnoy.
Yes.
I'm not Apalkov, but another one.
Okay.
In this bilayer, in this Dichalkaginite and valley thing, you can also imagine of weakly connected two layers, for example, where you can also have kind of similar. Maybe it will give you more insight in some sense if you add an additional size quantization level.
Yes. Yeah.
To compare and extract more parameters. I don't know. I'm thinking it's quite fascinating with the valley one, but probably you can add an additional level because like when you have a bilayer, you have symmetric and antisymmetric and things like that.
Yes.
What do you think about it? Yeah.
Yeah, thank you. So you're completely correct. So when you have two size quantizations like symmetric or antisymmetric or different subbands, so this is in some sense, once again, another degree of freedom similar to the Belly one. But in the Belly degree of freedom, something is different because in the layered structure, there is a strong Coulomb interaction between the layers, electrostatic. So here it is absent. So the physics is really similar, but some things are really different. So, of course, so we would look at these papers, and I guess it was a work. So the last author was Berkshire, but he was actually the one who wrote the samples in 1999, where the two subbands, they also observed like these phase transitions.
Yeah, that was partially caused by
Yes.
experiments. Another question with valleys and this, I might have lost my attention at certain stage, but it's known that in the kind of Dirac systems, your Landau levels not start from one half, but straight from the bottom of the valley. Is there any, you are looking at a different phenomena, but
Yes.
is there any manifestation or what happens?
So
Because
here,
if you just look at a graphene with a gap, you notice immediately that despite having a mass, Landau level starts exactly from the bottom.
From the bottom, yes.
And it is from either A or B, and there is a splitting and things like that. Maybe I missed.
So
because
here,
it was kind of crowded at the end, and
because
and
well, the
everyone
time was
was
running.
tired. Yeah, I know. So, is there any manifestation of that? I mean,
No,
now
we don't.
everyone knows it, but previously it was fascinating to see that they just massive particles, but there is no one half.
Yeah. So we are working in the structure with the quadratic band. So in our case, the Landau levels, they are pretty much simple. So they are equidistant. So this is
Yeah,
the
they are
quadratic band.
equidistant. I do not deny that they are equidistant, but the point is that they start not from H omega cyclotron over 2, but straight from the bottom of the band.
But this system, it has the gap.
And then they are equidistant because
so
of the parabolicity. It's just because the Hamiltonian is matrix rather than a single particle.
What is your question, Misha? I don't understand.
If you just put yourself plus delta minus delta on graphene,
what happened?
then there is no H omega over 2.
Yes, I
Maybe
understand, but what question to Anton? He didn't do.
is it somehow possible to see it in that experiment?
Okay, I don't know. I have to think a little bit about
That
it.
there is no offset.
Yeah, okay, I have to
But
think
in
about
graphene
it.
there is a problem with relaxation time. So here all frequencies are 100, about 100 gigahertz, but in graphene, especially in graphene,
I'm not talking about graphene. I'm talking on
What?
system described by matrix like graphene with a gap. There is a parabolic dispersion near the gap, which gives you equidistant Landau levels. But they do not start from H omega cyclotron over 2, but start from the bottom of the gap. It's a trivial mathematical exercise that there is no kind of zero oscillations. And
Yeah, I
the
understand.
limit is that, of course, whatever small is the gap, if you open it and there is kind of 1/2, and then you will immediately get a jump, whatever the gap is, and this jump is not observed. The gap is slowly opening, but the Landau level started from the bottom of the gap. I think that it is a trivial mathematical observation, but not everyone is seen. If it can be kind of seen in this type of experiments with polarization of, with valley ferromagnet and spin ferromagnet or something, if it would, how it influences, that is the main difference in my view of, say, Landau levels in dichalcogenites comparing to Landau levels in traditional semiconductor.
Okay, I
I don't
understand,
know.
but I
I'm
have
just,
to think a little bit about
yeah,
it.
I don't want to, if there is not observed, but it just a fact which, because it's interesting to see, because very often old people like me started to say that what is the point? It was all done in 80s and 90s. Why dichalcogenide is better for quantum Hall or for this or for that than a traditional two-dimensional electron gas when mobility was a million and it was much better
Yes.
quality structures and things like that. I try to, despite of my old age, answer that there is some different physics which not everyone realizes, and that was what caused my question.
Okay,
Yes,
I
that's
understand.
it.
Thank you.
Yeah, maybe we should talk by email and have a Zoom meeting, and probably I don't know. Never mind. That's fine. Thank
But in reality, I guess that the problem is in quality of the 2D materials which we have in Russia, for example, at all. So in every group we don't have good quality material, so to observe effects like Anton measure. So this is a real problem.
Yeah, partially. Yes.
Okay, a small educational question, probably missed it from the top, but in Algas quantum wells, are the valley and spin degrees of freedom coupled or decoupled by similar direction?
Well, they might be coupled, but we do not observe it. So the spin-orbit interaction, we have measured it in these structures. We know the value. It's like around 5 milli-electron volts per angstrom. So it's not really that large. It's, well, like in gallium arsenide. Well, but we do not observe the coupling between the spin and valley degree of freedom here in our experiments.
Okay, if you don't have more questions, then we'll send them. And let me give you a sign of our center as a
Thank you.
person who made it all.
Yeah, thank you.
Спасибо.
Всем спасибо. О, даже 4 человека. Кто был? А, тебя вот еще.
даже не совсем то же самое.
Сейчас. Запись.